Okay, so I want to focus you guys on some parts of the anatomy of the respiratory system that we did not cover yesterday, specifically the diaphragm. But just a quick recap, I'm going to use my tool right here. You do not need to be using the Jamboard right now. We're just doing this all through Edpuzzle because there's not much interaction you can do with the next slides that we'll be presenting to you. So let's see. The air flows either through the nasal cavity or the oral cavity, passing by the throat, down the voice box into the main windpipe, and eventually it reaches a fork in the road where it goes into one of the two lungs via the bronchi, which are the second largest air tubes. Those large air tubes are broken down into way smaller tubes called bronchioles, and bronchioles end in air sacs. So you have little tiny twig bronchioles ending in these grape-like clusters called alveoli. And just for context, you guys, there are about 400 million alveoli in your lungs. So let's go ahead and take a look at this animation on alveoli. One more time. Zooming in even further. All right, kind of looks like popcorn. All right, so let's move on now to the diaphragm. The diaphragm is actually a really cool looking muscle. It looks like a parachute. It's very thin and dome shaped, and it pulls in and out, expanding your lungs and contracting them to pull in air and to push out air. Pull in, push out. Inhale, exhale. And when it contracts with a spasm, that's when you get hiccups. And you also incorporate your larynx in that. That's where you get the sound with the hiccups. Okay, so that's your diaphragm. It just is in control of your lung capacity. All right, next. Your respiratory pathway is lined. So all of these major air tubes are lined with cilia, which are little itty bitty hairs, and they're covered in sticky mucus. When mucus is healthy, it's yellow. When it's infected, it's green. And it has a very important job in keeping you healthy because the only thing you want in your lungs is air. If you get water in your lungs, you drown. If you get bacteria in your lungs, you get an infection. Same with a virus. Okay, so you have to be able to keep your lungs pure and clean. So I want you to listen for these two questions and you'll answer them in the Edpuzzle. Why do we need mucus and how do mucus and cilia work together? So how does the hair and slime or snot work together? Let's go ahead and watch this.
The air we breathe contains foreign matter such as dust, bacteria, and pollen. Hair-like cells called cilia, as well as goblet cells, can be found in the lining of the respiratory tract called the respiratory epithelium. Goblet cells secrete viscous mucus that forms a layer to trap foreign material. The wave-like action of the underlying cilia mobilizes the mucus layer, removing the foreign matter and preventing it from entering the lungs.
All right, so cilia and mucus are very important. If for some reason they are unsuccessful in keeping bacteria and virus out of your lungs, then your body will move on to its next line of defense, which is to give you a fever, which is to zap the bacteria and virus with heat. You don't want that. That means that this failed. This is your first line of defense. Okay, next. Now, I often ask my students, why do we need to breathe? And they often say, so we can get oxygen, which is kind of the same answer or the same question. Why do we need oxygen? So let's focus on this chemical equation. Like, whoa, I'm already confused. I don't like science. Let me break it down for you. Food, and it can be any food, it doesn't have to be sugar. It can be protein, it can be fat, it can be carbs, which is sugar. Sugar in the presence of oxygen, and all of your cells will produce carbon dioxide that you breathe out, water that you urinate out, and energy to do your cellular functions. So like, let's say you're a liver cell, you need energy to detoxify your blood. Okay, so you need oxygen to your cells so you can make energy. All right, so let's see. This is going to happen on the cell level. It's really in your body. What needs oxygen are all trillions of your cells. And there's more if you're taller and there's less if you're shorter. So your cells need oxygen. And if the cells are working, then the tissue's working. If the tissue's working, the organ's working, the system that it's part of is working, and ultimately you are working. So you need to get oxygen to your cells. Okay, and they are going to be the fuel that's going to cause you to convert your food to energy. How are we going to do that? Well, you have to have a cardiovascular system. The heart pumps the blood, and the blood is the transportation system. It'd be like having your lungs as Amazon and not having a delivery system. That would be pointless. So it's pointless to have your lungs without your blood. I liked this because it shows like a museum quality. Here's like the legs, and here's the trunk, no head, of what all the blood vessels would look like if they were out of your body. You can see there's the femoral artery right there, very large and very small blood vessels on your body. Here's a medical picture. All right, so you need blood. Okay, so let's focus now on one of the 400 million air sacs in your lungs. So this picture is simple. I want to keep this super simple. What happens in your air sacs is this is where your air sacs meet your bloodstream. This is the most important spot in your body before you're breathing. So I'm just going to put right here, hello, or I'm just going to put hi. This is where your blood and your oxygen meet. So oxygen that you breathe in diffuses into your blood, and the waste that it produced diffuses out your mouth and back into the atmosphere and goes to a tree and it gets converted, yada, yada, yada. So oxygen comes in here and it attaches to red blood cells. Okay, next. This is where it gets cool. You have red blood cells. So here's a real vial of blood. Remember, red blood cells, actually the proportions look a little bit off here, but they're not the majority of your blood. For the average, it's about 45% of your blood. So look at this red part. This is after it's settled with density. So this is what it looks like before it's been on the desk, and this is probably a couple hours later. This is heavier, that's lighter. So just picture one cell in there. There's probably trillions of cells in there, but just try to picture one. On your blood cells, you have this protein called hemoglobin, and it's probably the most important protein in your body. Now, this picture is flawed, you guys, because every red blood cell has millions of hemoglobin proteins. So let's just focus, though, on one. It's a square-shaped protein. There's different shapes of proteins. This one's a square, so I'm going to label this right here. This is going to be my hemoglobin. Right there. Okay. So hemoglobin has 4 places for oxygen to attach to. So let's just take an analogy. Pretend like there's just one hemoglobin. The red blood cell is the oxygen Uber that carries oxygen to your body cells, and it has capacity for 4 passengers. Those 4 passenger oxygens can be in each of the 4 corners of the hemoglobin molecule. But they need to be attached there or they're going to fall out. They need a seatbelt. So this analogy actually works really well. So on a hemoglobin molecule, you have to have something that keeps the oxygen there, and that's going to be an atom called iron. So just what do I mean by atom? Here's a periodic table of elements, and these are all of the atoms on the planet. Iron is right there. It has a chemical symbol of Fe. And it's magnetic. And it's magnetic, not to the fridge, maybe to the fridge. I don't know what one that is at this point. I used to. Iron is magnetic with oxygen. So oxygen and iron get along really well and they're attracted to each other. So you need a lot of iron on your blood. In fact, for each hemoglobin, you need 4. Let's go back here. I'm going to put my text box right here. I'm going to put Fe, capital E, F, lowercase e. And they go in the 4 corners. So this is why you need iron in your diet, so you can transport your oxygen. So iron is going to be very important in your body. So iron, Fe, iron, is needed to transport oxygen to your body cells. Okay. So we have iron here. Let's go ahead and I'll just take my pen here. I'll take that. I'm going to put an oxygen, 1 passenger on each iron. So if I don't have iron there, you guys, I'm not getting enough oxygen. And if I don't get enough oxygen, I'm not going to feel very good. Okay. So that leads me to the next point. There's a condition called anemia, or you might be anemic. Let me ask you these questions. Do you feel tired all the time? Are your hands and feet always cold? You're always short of breath? You always feeling sick? Pica, this is one that's interesting. That's when you crave weird things like concrete and paper. That's your body telling you have an iron deficiency. I actually think ice might be on here too. That's telling you you need iron. For me, my sign that I need iron is I crave red meat because it's rich in iron and I'm a meat eater, or dark leafy greens have iron. Or you have this palar, which means you have a really pale lower eyelid compared to these supple and red ones, okay? So what causes this is two things. You either have too few red blood cells, not enough oxygen Ubers, you're not going to get oxygen to your cells, so you're not going to feel good. Or you do have sufficient blood cells, you just don't have enough iron um, present to transport your blood. So it could be an iron deficiency or it could be a hemoglobin red blood cell deficiency. But either way, that's anemia. And for these reasons over here, if you don't have iron or hemoglobin, you can't get oxygen. And you can't get oxygen, you can't get energy. Okay. So if you feel that way, sometimes the best thing to do is just to try to fix anemia by getting your body more iron through iron-rich foods. Sometimes it can get really bad, you guys, where you might have to have iron infusions or you can take iron supplements at the nutrition vitamin shop, but usually you can treat it dietarily. Okay, so that is the end of our respiratory lesson.